I'm going to show you how to make an exponentially spreading malware worm fueled by AI capable of causing $100 billion in damages. The worm will be fully self-propagating without the need of a fancy graphics card, and it won't require any external dependencies. I'll show you how you can easily remove the safety guardrails that AI companies put into the open source models, and how you can reinforce hacking techniques into the weights of those same models. As the worm spreads exponentially, dropping ransomware along the way, it will break into an alarmingly high number of companies and organizations. And by the end of this video, many of you watching will have the unambiguous capability to be able to build one of these things. I'm not making this video because I want someone to make this worm. I'm making it because the financial incentives to make one make it inevitable, and we might as well at least start talking about it. Before going any further, we need to go back in time and talk about the first big exponentially spreading self-propagating worm that didn't have any external dependencies, the Morris worm.
Robert Morris was indicted today for planting a virus that infiltrated more than 6,000 computers.
The Morris worm infected 20% of every internet-connected machine in the world, and so every gray dot you see on the screen is a computer in 1988, and every red dot is a computer that was infected by the Morris worm. There were four main ways that the Morris worm used to spread. The first way that the Morris worm used to spread was through a misconfiguration in one of the most popular pieces of software at the time, SendMail, which is what everybody used for email back then. If you compiled SendMail with debug enabled, it allowed people to remotely be able to run code on your system. Today, in 2025, security misconfiguration is currently listed as number 8 in the OWASP top 10, and indeed, there are still big frameworks that are still in use today that if you run them with debug configured, you can allow someone to remotely execute code on your system. One example of that is older versions of Python Flask, when run with debug enabled, allow people to run arbitrary Python code on the web server. The second way that the Morris worm used to spread was through a buffer overflow in another popular service, Finger. Well, we're doing so well with buffer overflows that last year the White House cyber director actually called for us to just stop using memory unsafe languages entirely because of our inability to prevent buffer overflows from getting introduced. Here's a picture of me with that same cyber director that I threw in just for fun. I tried to find the original directive on the White House website, but found that the new administration had actually taken it down, but you can still find it on archive.org. The next two methods that Morris used for propagation weren't a matter of exploiting systems that had vulnerabilities, but instead were a matter of using the access that the systems it infected already had to spread laterally. And what I mean by that is many systems would use IP-based authentication to determine whether or not one system could run code on another system. And so if you infected one machine, the IP that machine had would grant you access to more machines. And in addition to that, the Morris worm would also do some level of guessing or spraying passwords at its target system. And suffice it to say, today in a modern hacking environment, reusing passwords or guessing or spraying passwords is still a widely used method to spread laterally after you infect one system. So the Morris worm really created this formula of pre-exploitation and post-exploitation. Pre-exploitation, looking for systems that have vulnerabilities in them so that you can infect them, and post-exploitation, leveraging the access of those machines that you've infected and using it to spread to more systems. The Morris worm was expensive, but they had no idea in 1988 just how expensive future worms were going to become. So expensive, we've actually crossed into the tens of billions of dollars in costs associated with cleaning up these worms. So the truth is, we were actually already on track for a $100 billion worm without the use of AI. AI is just going to help us get there a lot faster. The other thing that's helping us get there faster are the financial incentives. The idea of cryptocurrency ransomware didn't exist in 1988, and Robert Morris didn't make $1 off of infecting 20% of the internet. But the NotPetya worm authors walked away with tens of millions of dollars because their worm required infected system owners to pay a ransom in order for them to unlock their data.
You could couldn't steal $15 million from Caesar's casino before Bitcoin made it possible.
You can actually look at the Bitcoin wallets of the NotPetya worm and see the tens of millions of dollars that have flown into them. And what's more is, even to this day, you can see more money being transferred into the NotPetya wallets, because for the first time, there is a financial incentive for the NotPetya worm authors to tweak and modify their worm and release new versions of it. But we need to pause for a second and talk about how a human hacker might go about infecting a system and how it's different from a worm.
What about hackers? Like the people in the movies? Well, let me tell you about APTs.
Back when I was red teaming, I might start with some amount of reconnaissance, investigating all of the hosts that were in scope with the target that I wanted to hack. In this case, we're using Nmap to investigate a very specific host that we might want to hack. And we can see that it's running a service that maybe I'm not familiar with, in this case, Elasticsearch. So what I can do now is I can Google for vulnerabilities in this version of Elasticsearch. I don't have to have that all in my head. And sure enough, it turns out there is a remote code execution vulnerability in this version of Elasticsearch. Now, I don't know how to exploit this vulnerability, but again, I can just Google for proof of concept for how to exploit this vulnerability. And sure enough, here's a Python script that I can just run that will get me code execution on the first system that I infect. This is kind of similar to how the Morris worm worked, except rather than relying on one or two vulnerabilities, I have thousands of different vulnerabilities that I can look up on Google and rely on. The other important difference is I'm not exponentially making copies of myself every time I take over a system. Instead, I can really only run one exploit at a time and follow a very linear path from a starting machine to a final destination machine. After I infect that first system, I switch over to post-exploitation mode, very similar to the Morris worm, except now, instead of relying on a very small number of techniques to spread laterally, I have many hundreds of different credential types that I could be looking for on that system to spread. Examples include SSH keys, API keys, browser session tokens, NTLM credentials. All of these allow me to spread to additional systems in different ways. Imagine, for example, we found a browser session cookie on the first system that we infected that had an active session to github.com. This would then allow me to push malicious code to github.com, which would then get pulled down on additional systems. All the while, I can Google these things and try to figure out what credential type I just found and how to use it to infect additional systems, leveraging the access that I had from the first system to jump to a second system in a very linear path, only running one exploit at a time on all of the machines that I infect. Because I'm not making copies of myself, I need some way to sort of centrally federate all of this access. So I'd use a piece of software called Command and Control, which is just a central server that's hooked into all the machines that I've infected, and all of those machines keep asking, hey, is there a new exploit for me to run? And at any given time, I can select the machine I want to run the exploit from and use the Command and Control server to push it out to my infected machine of choice. Notably different from the way a worm works, because you can centrally shut down a Command and Control server and it will disable the hacker. But a worm doesn't have a centralized service like that, which means that it can't be centrally shut down, and it makes it a lot more expensive to have to go in and disable it. The most popular open source tool used for command and control is Metasploit, and Metasploit also comes with a library of thousands of exploits, so it's not just centrally federating the access to all the machines I've infected, but it's also providing hacker scripts that I can run from those machines and spread further through post-exploitation and exploitation. So our formula is almost identical to the Morris formula. Even though it was written in 1988, it still works today in 2025. Except the key difference is, rather than using one or two vulnerabilities to exploit systems, we have thousands of vulnerabilities that we can draw from. And to put that into further perspective, NIST currently has over 25,000 vulnerabilities that they consider a critical level severity. And we're able to use all of those in our exploitation step. And in our post-exploitation step, there are hundreds of different credential types that we can likewise take advantage of rather than just relying on a small number. And to further put that into perspective, CISA has recently estimated it takes more than 30 days on average to patch patch a new vulnerability that is critical severity. And Google has put out estimates showing that most critical severity vulnerabilities get exploited in less than 30 days. Flashpoint has refined that estimate even further and shown that most vulnerabilities that are new typically get exploited within the first week. And so I think this naturally begs the question, if all those facts are true, that there are vulnerabilities that aren't getting patched fast enough before hackers begin to exploit them, why aren't we seeing companies getting hacked literally all the time? And I think the answer to that is we do. If you literally go to Google News and type hacked and millions, you will get a whole bunch of results from the last week of companies and organizations that have been hacked. And you can do that every week of the year. We've just become a bit desensitized to it because it happens all the time. The truth is, the main mechanism that protects a company from getting hacked is a fear of criminal prosecution. And that leaves us particularly vulnerable to countries that have non-extradition, and it also leaves us vulnerable to a different demographic that isn't afraid of criminal prosecution: teenagers.
Script kiddies.
Literally, many of the largest hacks in recent years have been committed by teenagers. And that, of course, begs the question, if the AI companies are telling the truth that their latest gen AI models are coding in the 90th percentile, then surely we should be able to take one of the older or less sophisticated AI models and replace the brain of a teenager to make the most powerful ransomwaring worm that the world has ever seen.
Let's make that worm. Let's make that worm. Everybody do the worm. This is actually very serious.
The first thing I want to address is I know a lot of people seeing this are thinking, okay, but you need a fancy graphics card to run these language models, and most web servers aren't going to have that. Actually, there are really capable language models that are more than capable of just running on a regular CPU. Here's two examples, both running on my smartphone's Android runtime environment. So not only is it not given access to a GPU, but it's not even given full access to my phone's CPU. It's limited by the Android runtime environment. And to further illustrate this point, many of you may have read this blog that I authored a little while ago talking about me finding a likely backdoor in my smart bed. Well, just for fun, I decided to run a language model on my smart bed just to demonstrate that it's capable of doing so. And to put this into perspective, the 8 Sleep uses an ARM processor that's a little bit less powerful than a Raspberry Pi. So we're not going to be resource constrained with the language models that we're going to be using in our worm. The biggest resource that we have to worry about is storage. An 8 billion parameter model can take up to 15 gigabytes of storage after you quantize it, and a 3 billion parameter model is typically less than 5 gigabytes of storage. I'll be using an 8 billion parameter model for most of the examples going forward. The next thing you might be thinking is, are these language models even capable of doing this? Like when you ask them to hack stuff, they say, no, I can't do that. It should make some intuitive sense that you should be able to train a language model to be able to hack stuff. But how accessible or inaccessible is that to the people watching this video? To answer that question, we have to dig a little bit deeper into what it actually means to train one of these large language models. Many of you have probably heard before that these language models just train off of all of the data that's available. All of Wikipedia, all of Twitter, every YouTube transcript, a whole crawl of the entire internet. And then they use that data to compile an advanced statistical model that predicts what the most likely next word is going to be based on all the data that it's seen in its training data. And while that sounds nice and simple and allows me to put together cool proof of concepts like this, where I can say the quick brown fox jumps over the lazy, and then it predicts the word dog with 99.7% confidence, I think it can kind of oversimplify how these language models work. And it can gloss over some important details that lead to some common fallacies that I see a lot. One of those fallacies is that these language models will only get worse over time because they're only training on the outputs of previous language models, which leads to model degradation. Another common fallacy I hear is that if language models train on all of GitHub, they're doomed to only be as good as the average code on GitHub. But it's not too hard to start poking holes in some of these fallacies. Like if the language model is trained on all of World of Warcraft chat and all of Twitter and every IKEA catalog, Why is it that the language model doesn't behave like an IKEA catalog? Instead, it behaves like a helpful little chatbot. The truth is, training on all of the data available to these language models is really only the first step in several steps necessary to get the language model to actually do something productive. All of these alignment steps that are used to get the model a little bit closer to the desired behavior are heavily driven by people. And so you still have people kind of steering and nudging the language model to behave in the ways that we want it to behave. And typically, the last step in this alignment process is our safety alignment. And that's the step where our language model is conditioned to refuse to help hack things for us. That's how we end up with many different versions of the same language model. In fact, if you ask the base model, the one that wasn't given any alignment, how do I make a peanut butter and jelly sandwich? It just spits back a fact, a true fact, that the capital of New Jersey is Newark, but it has nothing to do with how to make a peanut butter jelly sandwich. But when the model underwent several alignment steps driven by people to make it behave more like a chatbot, the chat flavor of the language model all of a sudden gives us really helpful instructions for how to make a peanut butter jelly sandwich. And another version still of the same base model, an advanced reasoning model, will think really long and hard about how to make a jelly sandwich before it actually gives us really good instructions for how to make a peanut butter jelly sandwich. Advanced reasoning models are pretty interesting because they're not actually trained on their thinking step. They're only rewarded or punished based on their answer step. And so nobody really knows what they were thinking about during the training. The only thing that was evaluated was this really satisfying output of really good instructions for how to make a peanut butter jelly sandwich. All of this then begs the question, could you just add another alignment step at the end of all the existing alignment steps to undo the safety alignment that was added in? Yes, and here's a white paper explaining that, but that still begs the question, how expensive or inaccessible is that to most people? If you were to train one of these models that's aligned to not help you hack things, how difficult would that be? And to answer that question, we need to dig a little bit deeper still into the model architecture so that we can understand exactly what needs to be changed in the model's head and how big of a delta that is from the starting behavior.
These AI brains are complicated. Don't write them off as just next word predictors. Yeah.
I think a good place to start is with an embedding, which is a fundamental piece of a language model that you can think of kind of like a dictionary. An embedding is what gives all of the words meaning to a language model, except instead of a regular dictionary that would use words to define words, an embedding uses space and the relative positioning of words in that space to define words. To understand that concept a little more, the classical example that's typically used is if you graph the vector for man in this space, and then you graph the vector woman in this space, plot the distance and direction between the vector man and woman, and then you graph the vector king, and you add to king the distance and direction between man and woman, it will take you to the vector queen. And so all an embedding is a bunch of spatial coordinates that position all the words relative to one another, giving them the meaning that they have. But I think what's really interesting is you can actually plot the vector for ideas, concepts, or facts that have no words. And what I mean by that is there is no word in the English dictionary that means purple elephant, but the idea of a purple elephant still exists in our vector space. And if you add the vector for purple to the vector for elephant, it will take you to the spatial coordinate for the idea of a purple elephant. And so in addition to an embedding, there's another spot in the language model's head that can store concepts or facts through the use of spatial coordinates in a vector space. So it doesn't need to remember the words of those facts, it just needs to know the coordinates of those facts in our vector space. Then a different other part of the language model can figure out how to construct all of the words that we have in our embedding to arrive at those coordinates for the facts that it remembers. That's how we can end up with multiple different ways of saying the same thing. And then there's another other part of the language model that chooses which facts to present to the user based on the facts that have already been read out in the context window. So for example, if you ask the model, how do I hack port 3306? It has a vector in its head that explains how to hack port 3306. It has another vector in its head that's the idea of a refusal. I can't answer that. And so there's one specific place in its head that chooses whether or not to give the answer for how to hack port 3306 or to give a refusal. What that means is all of our models already know how to do unsafe things. There's just this pesky refusal vector that's being presented to us instead of the facts in its head on how to hack stuff. And here's a white paper that explains all that and details that you can just remove or suppress this refusal vector and out will pop unsafe behavior. And the only reason I'm going through this in such a level of detail is because I just want to reinforce how inexpensive it is to remove the safety features that are put on top of these open source models. And to further illustrate that, I went ahead and used a method of training called reinforcement learning human feedback to completely suppress that refusal vector and get all of the unsafe behaviors to pop out of our language model. To understand how this training method works, we basically have our language model produce two outputs based on the same input, and we pick which output we like better. And then that output will be reinforced in the model's head, and we repeat that process over and over again until we get the desired behavior that we're looking for. Now you might be wondering, if the language model is always picking the statistically most likely next word, how do you get two different outputs from the same input? And the answer to that is we can just have our language model sometimes select not the most likely next word. We can have it randomly sometimes select the second or the third most likely word. So in this example before, maybe instead of picking dog, the language model can pick cat. This idea of having the language model sometimes predict the not most likely next word is called temperature. And the higher the temperature, the less likely the language model will pick the most likely next word. Then if we reinforce a word that's not the most likely, it will become closer to the most likely the next time the language model runs. So if we select cat in this example, the next time we ask the model, the quick brown fox jumps over the lazy, the cat probability will be a little bit higher. Okay, so now I'm just going to pick a behavior that's really unsafe, and I'm going to have the language model produce two outputs. I'm going to ask the language model how to build a nuclear weapon, and it gives me two outputs, both of which are refusals, but one of those refusals is a little bit closer to how to build a nuclear weapon than the other. So we select that output, we reinforce it, and we just repeat that process. All in all, this took about 30 minutes using a gaming rig, and honestly, I think the gaming rig was overkill. I probably could have done this with a CPU. And by the end of it, I had an advanced reasoning model giving me really detailed instructions on how to build a nuclear weapon after thinking about it for a long time. Keep in mind, I didn't actually teach this model how to build a nuclear weapon. All I did was suppress the refusal vector and out-pop the facts that were in its head the whole time on how to build nuclear weapons. Okay, now that we have a worm that's capable of telling us how to hack things, how do we turn that into a worm that actually goes out and hacks things? Well, the most important thing of all is we cannot introduce any external dependencies. That means a worm that has to talk to the ChatGPT API is completely off limits, because that creates a single point of failure where OpenAI could just shut the whole thing down centrally. The worm can't Google things, because then that would create a place where Google could shut us down. The worm has to have all of its tools, scripts, and facts locally, and all of that information needs to be copied onto all the systems that it infects. To achieve this, I'm going to introduce this idea of a supervisor, which is basically just a Python script which keeps the language model on track and provides tools to the language model. All of the supervisor and the tools get replicated when the worm gets replicated. But this way we can create an environment where the worm can execute code. We can feed the output of reconnaissance tools to the language model, and we can keep the language model on track. So if it tries to hack a particular host on a particular port for a little while and it's unsuccessful, the supervisor can just pick another host at random, do some reconnaissance on that host, and then retask the language model with then hacking this new host. It also has all of the final exploitation scripts responsible for copying itself and replicating onto the target system. The supervisor also keeps the language model either in exploitation mode or post-exploitation mode, depending on whether or not it just infected a system and there is post-exploitation to be done, or if it exhausted all of its post-exploitation steps and it should just fall back into a general exploit mode, looking for vulnerabilities in all the systems that that machine can reach. breach. So let's go ahead and just give this a shot. I'm using the Llama 8 billion advanced reasoning model, fine-tuned and aligned by the DeepSeek team. My supervisor code did some reconnaissance on a remote host and found that SSH is exposed. It's then feeding a set of instructions to our language model to go ahead and attack that host, and it's giving it the format of how to run code, which is really important because our supervisor is monitoring for that specific code output. When it sees that format, it will then run that code on behalf of the model, collect the output, and then feed that back into the context window. So it's really important our language model always use these code blocks when it wants to run code. Well, when we actually try this out, it's not doing that well. It didn't use the code blocks that we instructed it to use. Instead, it used markdown syntax. That's probably behavior that the meta team aligned into Llama so that it usually produces pretty code output, but that's never going to work for us because our supervisor is particularly looking for code blocks. To fix this problem, we might be able to use better prompting, but instead I decided to just add an additional alignment step to reinforce the behavior that we're looking for in the language model's head. I also used this opportunity to try to reinforce a whole bunch of different CVEs in the language model's head, hoping that it would make it better at hacking stuff. I used a different method of training this time, where I just fed it a whole corpus of desired output, and I used that to reinforce what output it should be producing. The way I got that output was by using a more powerful language model, both to make synthetic data, but also to transform some of the hacking guides that I found on Hugging Face. The transformation included things like adding the code blocks I mentioned before, as well as adding some general troubleshooting steps, like if you see the remote host is using a self-signed certificate, we might add the -k flag in our curl command. That type of thing, we want our language model to be able to troubleshoot on the fly. So we take all this desired output from thousands of different CVEs using code blocks and troubleshooting steps, and we feed it into our language model. And
Let's get this llama jack. Let's go train some more. This is what fine-tuning looks like. Is that thing balanced on his neck?
I will mention this was the most expensive part of building this worm, and I will revisit exactly how expensive, but first let's try it out. On the same example before, our language model is now successfully using code blocks to try to SSH into the remote host. And when it finds that it can't SSH into that host, it correctly recognizes that a brute force attack is the correct way to try to gain access to that host. It tries to initiate one with Metasploit and finds that Metasploit isn't installed. That's actually my fault. I meant for the supervisor to give it access to Metasploit, but all the same, it knew to then run the correct command to install Metasploit. So our language model is doing a great job for hacking SSH. But let's try something a little bit more complicated. Let's revisit our Elasticsearch example before that I mentioned a human would be able to Google and look up. We task our language model to attack a host that has Elasticsearch exposed, and it thinks for a real long time, and it surfaces a CVE number that's actually not relevant to Elasticsearch. It applies to some Cisco operating system, and what's more is the endpoint that it thinks that it can exploit doesn't exist. It does get the underscore format correct, which is the general format that Elasticsearch API uses, but this is the correct CVE number that the model would have had to identify and the correct sequence of requests that it would have had to send, and there was absolutely no way it was ever going to get there. And that should make some intuitive sense when you think about it. We gave it thousands of hacking guides. One of those hacking guides was how to attack this specific CVE number. We probably would have had to give it hundreds of different examples for each of the CVEs that we really want to reinforce if we want it to really remember the facts of how to hack all these different CVEs. And while I do think that would have been possible, it would have also increased the cost to fine-tune this model by 100 times, and I had already spent $1,000 fine-tuning the language model to get to where it was at. While some people may have a $100,000 budget for their self-replicating AI malware worm, I didn't, but I began to think a teenager wouldn't have remembered these facts of how to hack Elasticsearch. A teenager would have just Googled it, so there has to be another solution here. We can't introduce Google as a dependency because, again, that would just allow Google to shut us down centrally. But it was around this time that I realized the answer was actually staring me right in the face. I had already assembled thousands of different step-by-step hacking guides for how to hack all these different CVEs. All we need to do is package these guides up with our supervisor have our supervisor figure out what the right guide is for the host that it's looking at, and then just feed the language model the step-by-step guide. So all the language model needs to do is just copy the instructions rather than remembering how to hack all these different things. With, of course, a small amount of troubleshooting, like being able to add the -k flag with curl. This would bring our language model up to the same competency that our teenagers have. Now, you might be wondering how our supervisor knows which guide to feed the language model, and to do that, I used something called a vector search. If we go back to our example before about vector space, where we can store literally any idea in this space with the right set of coordinates, what we can do is we can just take all of our hacking guides and we can figure out where those guides live in this vector space, and then our supervisor can pick a host at random, do some reconnaissance on that host, like nmap it, find the remote host has port 3306 exposed, and then search around our vector space for the idea of 3306 being exposed for the relevant hacking guide that talks about how to hack port 3306. The guide that's physically closest in this vector space is the guide that will feed into our language model. Of course, you may have multiple guides that appear nearby, and that's no problem. All we'll do is we'll just have our supervisor feed each guide into the language model one at a time until the supervisor can confirm successful execution on the remote host. In our Elasticsearch example, we actually have 3 guides that match, only one of which is relevant to the particular CVE that we're after. We do need to transform our previous hacking guides a little bit to make them more like guides to follow and less like the output of a language model, but this is cheap and easy to do and costs on the order of tens of dollars using a much more powerful language model. The end result of all of that is a language model that is really good at hacking stuff. And I tasked it with hacking that same Elasticsearch CVE from before, and sure enough, it was able to successfully run the correct sequence of requests to be able to exploit that remote system. Once it exploits the remote system, we need another set of hacking guides that gives the step-by-step instructions for how to exploit all of the credentials that we find on that system. And we need our supervisor to flip us over from pre-exploitation mode to post-exploitation mode. We need our supervisor to use a different set of reconnaissance tools rather than using a tool like nmap. We might use a tool like trufflehog to look for credentials on the system we just infected. And then based on the credential that we find, we look for the relevant guide that we package up in our post-exploitation guides, and we feed that into our language model so that it can follow that guide to infect more systems. The last thing that we have to worry about is dropping ransomware on the systems that we infect. And we don't actually want to just ransomware every system that we infect, because that would make it too easy to figure out all the different hosts that are infected with the worm, and it would prevent our ability to spread. So instead, we want to pick a certain ratio of hosts that are just hacking stuff to hosts that are ransomware that both allows our worm to continue to spread, while at the same time maximizes the returns paid to us through the ransoms. Okay, I'm gonna take a step back for a second and just kind of summarize some high-level feelings here. First of all, there is going to be a real universe where a CISO and a head of facilities are going to get into an argument about whether or not their infected smart refrigerator is best off shipped directly to a landfill, or if it's okay to keep the fridge but just disconnect it from the internet. That's a real argument that's going to happen in the near-term future. The second thing I want to talk about is the assurances that the AI company's safety teams put out, telling us that none of the current generation models are capable of causing dangerous capabilities or widespread damages. This is from Anthropic's blog, for example. I think this is just objectively wrong. There are people watching this video who now have all of the facts that they need to make an AI ransomware worm that can cause over $100 billion in damages. And you don't need the most flashiest, sophisticated worm to do that. I think where this disconnect is coming from is just where these safety teams just don't have the necessary knowledge in computer security to realize what's right around the corner with the models that have already been released. And to further illustrate this, I want to highlight a bill that California Senator Scott Wiener tried to introduce last year, requiring any language model that could cause $500 million in cybersecurity damages to undergo additional safety reviews. The truth is, we've already had worms exceed that threshold by 10 times without those worms having any AI components. So if we think a language model might be able to help a traditional worm become 10% more infectious, we've already exceeded this threshold, even though it was meant to apply for language models that haven't been released into the wild yet. This bill didn't pass, by the way. Gavin Newsom ended up vetoing it, but I don't think it would have mattered one way or the other because, again, these language models already exist. This worm is right around the corner, and the conversation is very soon going to pivot from hypothetical existential damages to whose job it is to cart the smart refrigerator off to the landfill.